more specific, the AC induction motor. By now, you should have a good knowledge of electricity and its application in the air conditioning industry. You know how electricity is generated and used, and you have been exposed to some of the devices that are used to convert electrical energy to mechanical work in air conditioning systems. The most important of the energy conversion devices is the electric motor. This module will provide a basic understanding of how a motor works and how it's protected from damage. Air conditioning and refrigeration systems use many different kinds of AC motors. It's important to be able to recognize and troubleshoot the various types. Why are there so many different kinds of electric motors? The answer is that different motors do different jobs. The selection of a motor is based on the amount of torque it must deliver and the speed at which it must run. When these two criteria are satisfied, power consumption is considered. Torque is the force that must be generated to turn a motor. A fan motor requires little torque. You can rotate the fan blade with a touch of your finger. A compressor motor, on the other hand, offers a great deal of resistance and therefore requires a higher torque. Also, it takes more torque to start a motor than it does to keep the motor running once it is started. That's why the same type of motor is not used to drive both the fan and the compressor. A motor with the ability to start under heavy loads is more expensive to produce and operate. To keep cost low, a motor should provide the lowest starting torque required for the particular job. Motor applications are summarized later in this module. But before we address applications, it's important to know how motors are constructed and how they work. All AC motors have a fixed or stationary element called the stator and a rotating part called a rotor or armature. The stator is, in essence, a coil of wire wrapped around a magnetic casing. AC voltage applied to the stator coil produces a rotating magnetic field. The rotor consists of copper bars or wires which act as conductors. They are mounted on a soft iron core. This core provides a path for the magnetic field of the stator. The copper conductors are shorted together by the copper end ring so that current flow can be induced. We discussed magnetic induction in Module 2. In a motor, the powerful magnetic field created by the stator induces a current in the copper conductors attached to the rotor. This current creates its own magnetic field. The principle of magnetic attraction and repulsion then takes over and causes the rotor to turn. Let's explore in more detail how the motor actually works. Here we have an iron disc located directly opposite a strong magnet. If we rotate the magnet and close the air gap distance, we will reach a point where the disc also begins to turn. This is not directly due to magnetic attraction or repulsion, however. The disc will turn because the rotating magnetic field of the magnet has induced an opposing magnetic field in the disc. This field produces an opposing magnetic field that interacts with the field of the magnet.
Strong magnet.
Here, the motor is represented by a permanent magnet rotor pivoting on a shaft. The two stator poles have wire coiled around them. Like the coils of relays and contactors, the stator coils produce strong magnetic fields when current flows through them. You will recall that like poles repel and unlike poles attract. Therefore, when the polarity is as shown here, the permanent magnet rotor will move towards the stator poles. As the alternating current in the stator coils changes direction, the polarity changes. North becomes south and vice versa. The rotor south pole and stator south pole repel each other, causing continuous turning of the rotor and shaft. It seems to work well, but let's look closer. If the magnetic rotor stopped in the position shown, we could not restart the motor regardless of the polarity of the two stator poles. Here, the rotor and stator poles attract, and no motion occurs. Even when the stator poles reverse, the repelling forces will be at such an angle that the rotor will not turn. A rotating magnetic field is needed to induce rotation. We can create that rotating field by adding another stator winding. Let's refer to this winding as the start winding, and the original one as the run winding. The start winding coils are made of lighter wire and have many more turns than the run winding. So, when voltage is applied to the windings, current buildup in the start winding is slower than it is in the run winding. The currents in the two windings are thus out of phase with each other, and enough torque is created to cause the rotor to begin turning. These split-phase motors are used in fractional horsepower applications because of their low starting torque requirements. The speed of a motor is determined by the number of stator poles and the frequency of the applied voltage. Increasing the number of stator poles lowers the speed, while increasing the frequency raises the speed. The speed is measured in revolutions per minute, or RPM. The maximum speed of the motor is also known as synchronous speed. The addition of a load causes some slippage or inefficiency in motor operation. The motors used to power air conditioning compressors and fans are generally rated at 95 to 97% of synchronous speed. To obtain higher starting torque in a split-phase motor, a capacitor is connected in series with the start winding. We discussed capacitors in Module 6. Let's take a moment to review how capacitors work. In an AC circuit with a purely resistive load, the voltage and current are in phase. They peak and cross zero at the same time. When a capacitor is connected into the circuit in series with the load current will lead the applied voltage. Comparing the waveforms of the previous example on the same axis, waveform A represents the voltage applied to both circuits, and waveforms B and C represent current flow through the resistive and capacitive loads respectively. Now, let's remove the voltage waveform. It's obvious that current in the capacitive circuit is leading the current in the resistive circuit. Let's see how this principle is used to help start induction motors.
Is that leading?
Here we have taken a motor condition with the rotor stopped between the two stator poles and have put a capacitor in series with one of the stator windings. When voltage is applied, the capacitor will cause the current through the upper stator winding to lead current through the lower stator winding. This causes magnetism in the upper stator pole to occur earlier than in the lower stator pole, and provides the initial push we have been looking for to start the motor. When the current flow in the upper winding reverses direction, the polarity of the stator pole also changes. The rotor south magnetic pole has rotated to the point where it is repelled by the stator south pole, causing continued rotation. A capacitor is selected for its capacity and voltage rating. Capacity is expressed in microfarads, abbreviated MFD. High MFD results from either using large plates or a small amount of insulation between the plates, while low MFD results from using smaller plates or more insulation. The voltage rating, which is stamped on the capacitor, indicates the maximum voltage that can be connected across the capacitor. If the voltage rating is exceeded, the capacitor is likely to fail. Capacitors used in motor circuits are selected to achieve the desired phase angle shift and to obtain the required current flow through the series load. Both of these characteristics are determined by the capacitor MFD rating. You will learn the significance of phase angle and current as we proceed further in our study of single-phase motors. AC induction motors use capacitors to provide a boost to start the motor and improve efficiency once the motor is running. As we mentioned earlier, a start capacitor is used to provide a high starting torque for large motors, such as those used in compressors. The start capacitor is switched out of the circuit as soon as the motor is running. A run capacitor is used on low torque motors, such as those that drive low capacity compressors and fans. The run capacitor remains in the circuit all the time to help improve the energy efficiency of the motor. If a run capacitor fails, the motor will draw about 10% too much current and may overheat. As you can see, all capacitors are not the same. Because the run capacitor is in the circuit all the time, it has large plates and a large amount of dielectric material in order to dissipate heat. The start capacitor, because it is quickly switched out of the circuit, does not have a heat dissipation problem. It is typically made from a rolled sandwich of metal foil and insulating material. This concludes our discussion on the basic principles of AC induction motors. Here are some key points you should remember. Torque is the force required to turn a motor. It takes more torque to start a motor than it does to keep the motor running. AC induction motors consist of a stationary part known as a stator and a rotating part known as a rotor. Induction motor operation relies on both magnetic induction and magnetic attraction and repulsion. The maximum speed of a motor is known as its synchronous speed. Placing a load on a motor results in some loss of efficiency, so the motor never runs at synchronous speed. Motors usually require help in getting started. That's why there are start and run windings. Capacitors are also used to help start motors. In a capacitor, current leads voltage. This creates a phase shift that gives the motor a starting boost. A run capacitor remains in the circuit, while a start capacitor is switched out of the motor circuit as soon as the motor is running. In the next segment, we will discuss the various types of AC motors used in comfort air conditioning systems, and we will examine the devices used to protect these motors from damage.
Hey, this shit's boring, dude.
But before you move on, complete the skills check that follows. Then, go back and review what you don't
It
understand.
seems kind of late, too, huh? What? The video? Yeah. Like, we're already using a lot of these start capacitors and then...
Now let's discuss how different types of motors work. The diagram of our earlier motor has been redrawn to show two coils or windings in parallel. A capacitor is in series with one of the windings. The parallel circuit is energized by power source L1, L2, as you will normally see in a schematic. The winding in series with the capacitor causes the motor to start, and so is called the start winding, S. The other winding is called the run winding, R. Point C is a common junction where the windings are connected to L2. The capacitor is designated RC to signify run capacitor. The run capacitor starts the motor and then is left in the circuit to improve running efficiency after the motor has started. The run winding contains the number of turns of wire required to obtain the best motor performance at a given line voltage. The start winding, as mentioned before, has considerably more turns than the run winding. A smaller diameter wire is used to pack this higher number of turns into the space available. The combination of small wire and many turns gives the start winding higher resistance and lower current carrying capacity than the run winding. These schematics represent three different ways of depicting the same single-phase motor. Although they may appear different, the three schematics are electrically identical. You might see any of these on a circuit diagram. This will help you recognize them. This motor is called a permanent split capacitor motor because the run capacitor is connected to both the start and run windings and remains in the circuit all the time. You will see as we proceed that other capacitors wired in this way are switched out of the circuit immediately after startup. The PSC motor has moderate starting torque and good running efficiency. It's used to power fans and some small compressors. The run capacitor has a relatively small MFD rating to limit current through the start winding. The low MFD rating also results in a small phase angle change, which explains why there is only a moderate starting torque. The capacitor start motor has a high starting torque, but is not as efficient as the PSC motor. It is used primarily as a fan motor. The reason for its lower efficiency is that the capacitor is switched out of the motor circuit